Hello and welcome back to Chemistry Time. In today's discussion, we are going to focus more on enthalpy. We'll discuss how we can use Hess's law to determine the enthalpy change of a reaction. We will also look at how we can determine the enthalpy of a reaction based on the enthalpy of formation of the individual components. Enthalpy, as we have mentioned previously, is a state function and is reliant on the amount of reacting substances and the physical states of the reactants and products. For state functions, we are not concerned with the path, but the initial and final states. This same concept is applied similarly when we add together two balanced chemical equations to obtain a net chemical equation. The change in enthalpy for this net reaction is the sum of all the enthalpy values for each individual reaction. This principle is referred to as Hess's law and allows us to calculate the enthalpy of a complex reaction. This is also a convenient way to calculate the enthalpy of a reaction without having to perform an experiment. The steps we will follow for determining Hess's law is to first identify the equation whose change of enthalpy is unknown or is the desired equation. Next, write out the remaining equations and known enthalpy values, and when added, will give the desired equation. Then we will arrange the equations in a way that when you add them up, the sum is equal to the desired equation. Keep in mind that if you reverse an equation, you must flip the corresponding sign of the enthalpy associated to that equation. In addition, if you multiply by a factor, you must multiply the enthalpy by that same factor. Finally, we'll add all the steps together to determine the overall change in reaction enthalpy. Let's take, for example, the following thermochemical equation and determine the enthalpy change per mole of carbon monoxide for the reaction of carbon monoxide with oxygen gas to give carbon dioxide given the following equations. Step 1. We'll write out the provided chemical equations and the desired final equation as well. Keep in mind we want CO to have a coefficient of 1. The balanced equation should be as follows. Step 2. We now need to manipulate the two equations to eventually add up to the desired equation. We do this by identifying what species must be located in the reactants and products. We must flip the first equation because we want carbon monoxide to be located on the left-hand side of the equation. We must remember to flip the sign associated to the enthalpy. We do not need to reverse the second equation. Next, we will multiply the second expression by 2 in order to cancel out solid carbon and gaseous oxygen. Keep in mind we must also multiply the enthalpy by 2 as well. We can now add everything down to see if it matches the desired final equation. The problem asks for enthalpy change for 1 mole of carbon monoxide, and in order to determine that, we must divide everything by 2, and the change in enthalpy is equal to negative 283.0 kilojoules. Hess's law also allows us to calculate the change of enthalpy of a reaction if we know the enthalpy of formation of reactants and products. The enthalpy of formation is the heat change that occurs when 1 mole of compound is formed from its constituent elements in the standard state at 1 atmosphere of pressure and 25 degrees Celsius. For example, the formation of carbon dioxide from carbon and oxygen. We denote standard state conditions by a degree sign superscript. It is important to point out that a pure element has a standard enthalpy of formation of 0, whereas standard enthalpy of reaction is the enthalpy released or absorbed by a given reaction. We can rewrite Hess's law for the standard enthalpy of reaction is equal to the sum of all the standard enthalpies of formation times the stoichiometric coefficients of the products minus the sum of all the standard enthalpies of formation times the stoichiometric coefficient of the reactants. Let's do an example for calculating the standard enthalpy of reaction for the following equation of silver 1 cation and the chloride anion to produce silver 1 chloride. In these types of problems, you will be provided a table of known enthalpies in order to calculate the enthalpy of reaction. The enthalpy of formation for silver 1 chloride is negative 127 kilojoules per mole. The silver 1 cation is positive 105.9 kilojoules per mole, and the chloride anion is negative 167.2 kilojoules per mole. We plug these values into the Hess's law formula, and the enthalpy of the reaction is negative 65.7 kilojoules per mole. I wanted to define a few other enthalpy terms you might encounter. Enthalpy of combustion is the change in enthalpy during a combustion reaction. Enthalpy of vaporization is the change in enthalpy for the vaporization of 1 mole of substance, Lastly, the enthalpy of solution is the change in enthalpy associated to a specific amount of solute dissolved in a specific amount of solvent. In today's discussion, we discussed how we can use Hess's law to determine the enthalpy change of a reaction using individual steps. We also looked at how we can determine the enthalpy of a reaction based on the enthalpy of formation of the individual components. Thank you for joining me and have a wonderful day. Thank you.